Right. So we took a look at the example in R using the small human resources data set, and we found that there were variables that were misspecified. So we went ahead and changed some of those. So, for instance, annual income, we changed that from being a categorical variable to be a numeric variable. We changed age group from a numeric variable to be a categorical variable. So that is very common. Um, the next thing we want to do is to talk a little bit about model degrees of freedom. When using dummy variable encoding, we have to be cognizant of the fact that this encoding increases the model degrees of freedom at a higher rate than using, let's say, label encoding, that which does is it makes the variable be numeric. So just remember that a numeric variable only brings in one degree of freedom, but each categorical variable contributes the number of degrees of freedoms that it contributes is equal to the number of dummy variables created. So in other words, if a variable, let's say rating, has 5 different levels, so the number of model degrees of freedom that are contributed to the model are going to be 5 minus 1. So the number of classes or the number of levels minus 1, because that's the number of dummy variables created. And again, it's just the new variables that are created, and that's what model degrees of freedom means. But I want to go a little bit more in depth into that particular topic. So before we used to see things when we were doing simple linear regression, and we usually plotted y against x, whatever that predictor variable was, and we generally used to see a plot that looked more like this, an x and a y, and then we kind of plotted the relationship that they had. Either it was checking if it was linear or, but it generally looked something like this. When you increase the dimensions from being one predictor to two predictor, then things become then instead of being just 2 dimensions, we have now three, what we call a three-dimensional space. So we have our y, we have our x, let's call it x1, and we have our x2. So with two predictors now we are at a three-dimensional space. Every predictor brings in an extra dimensional space if it is a numeric predictor. So what that means is if x1 is a numeric predictor, then it will have that extra dimension here. But if, let's say, we bring in a variable that is categorical, well, each of the dummy variables that is created creates an extra axis, which means that increases the dimension. So if we have, let's say, a variable x, and that variable has 3 classes or 3 levels, A, B, and C, then just that single variable creates a three-dimensional space like this one that we are seeing here, because we would have to leave out one of the levels to be, let's say, the base, and so let's say we select this one to be the base, but these other variables need to have their dummy variables created. So let's say we have a dummy variable for B and a dummy variable for C. Each one of those is going to be have the values 1 or 0, but they, even though they have only 2 possible values, they still create an extra axis in this dimensional space. We can only look at 3 dimensions at the same time. So if we were to visualize adding more variables, it would be like thinking adding extra space, extra axis into these dimensional space. It's not possible to visualize that in that way. But just think about it this way: the more variables we have, the higher the dimensional space. And now, if we have categorical predictors, then they actually add a little bit more than the numeric predictors. And exactly, it will be the number of levels of each predictor minus 1, minus the base. So each predictor brings in that many dimensions, extra dimensions to the problem. When is that a problem? So why do we care about that? Well, there's something we call the curse of dimensionality. In the curse of dimensionality, let me explain it this way. Let's say we have a variable x, and it can only take the values from 0 to, let's say, 2. And those are the possible values that that particular variable x can take. Generally, the distance between the points is, in absolute value, is just the difference between one value to the other, is not that much. If you think about it, let's say the distance between a given GPA to another GPA in numerical values is not that high generally. And what happens is that when we increase the dimension, let's say we create another dimension B, and that dimension B has the same units. So has the same range of values from 0 to 2. Now, what you see is that when you plot, the distance between the points actually start to become a lot larger. Okay? So, whether you measure the distance instead of, Euclidean distance or whatever metric, the difference between the points, but actually each point will be further away from each other than if they were in one, dimensions lower. Now, when we go now through 3 dimensions, dimension A, dimension B, and dimension C, the points actually become further and further away. And actually, there are mathematical proofs that show that if you just take a range of value, let's say from 1 to 2, the number of points that are captured in that range, as the dimensions go higher and higher, the percentage of the points is actually lower and lower, which means, in other words, that the points get further and further away as the dimensions increase. Okay, just keep that in mind. That's not something that we're going to test about or ask you to know, but all I'm trying to get you back is this problem. So what happens is, as we include more variables to the model, that increases the dimensions. The points become further and further away. Now, the problem here is that we need many points in order to be able to create a plane, which is what we are doing in our prediction. Okay? The plane can be linear, or it can be something like this, which is a nonlinear plane, which we will look at when we talk about quadratic effects. But what I'm trying to say with this is that if the points are very scattered, such as this graph right here, then it's more difficult for the model to find the correct plane. Even one point that looks like that deviates a little from the rest, can make that plane just tilt too easily. Okay? That is called, that's what the curse of dimensionality tells you. And we will see that it is a big problem when we have especially just a few points. The higher the dimensions, the higher the model degrees of freedom, that means the number of variables that we bring in, then the more points we need in order to be able to determine where the plane actually is headed. What is the correct plane, how the plane looks like in that space. We don't want to have a situation that the points are so far away like this. So what that brings us is that we have to be careful in the number of model degrees of freedom that we bring into our models. Just remember, numeric variables actually bring in 1 degree of freedom each, but categorical variables bring in the number of levels minus 1. Okay? So if we have, let's say, a variable such as, let's say, state in predicting, let's say, salary, it might be that the variable is good, so it justifies the extra amount of degrees of freedom brought by. So again, think about it this way. If, let's say, we think about 50 states, we would have 49 degrees of freedom, which increases the model degrees of freedom. That means that every one of these dummy variables created actually increases the axis by 1. The axis of, it increases the dimensionality of the problem. So we need to have more points. In that case, where there is a lot of degrees of freedom, then we need to have more observations so that the model can actually derive a correct plane. Okay. Now, having said that, I don't want to say that categorical variables are bad. Not at all. If the variable has predictive power, then that justifies bringing in more degrees of freedom. Now, the only case, so we have to balance that. We have to balance the amount of predictive power that the variable brings with the complexity that the model brings. That actually is not such a big problem in simple linear regression, or well, in multiple linear regression. But sometimes when you go to more complex models, when you include quadratic terms, when you start including interaction terms, which we will talk later, then that actually starts creating a problem where more points, more observations are needed. So just be cognizant of that, right? So we'll go to an example where we start talking more about interpretations of the categorical variables and what they really mean. All right.